Here I'm going to talk about a system called NightWatch. It is an extension of the Malloc system. It helps the Malloc system manage the CPU cache when doing the memory allocation. Here's a common view of the Malloc system. As we can see, the design is targeting on the memory management and has nothing to do with other hardware resource allocations. However, this is not the whole picture. Actually, many of the hardware resources are physically indexed, so such as the DRAM, CPU cache, memory bank, and so on. So the mapping between these hardware resources are the statics. So once a piece of physical memory is allocated for the user's program, the other hardware resource allocations, such as the CPU cache, is also settled as well. So from this point of view, a Malloc system is not only a memory allocator. It should be better to work across multiple hardware layers. And this work is to integrate the CPU cache management into the Malloc system. So let's first look at how the cache resource is being allocated during the memory allocation. If the operating system allocates a piece of physical memory for the user's program, it tends to map the consecutive page frames to the virtual pages. And this helps the user's data spread across every cache size. And this approach can be benefit for the data chunk which has a strong access locality. However, not every data chunks are cache friendly. Here we examine a set of programs in a benchmark set. We record the cache miss rate of each data chunk. As we can see, the access locality are very different between the data chunks. And for some programs, there are even a large portion of the data chunks have a very high miss rate, even above the 90%. So this part of the data chunks not cache friendly. They actually cache polluters. So if we load this data into cache, they will not get reused before eviction, and they just take the available cache space and replace the strong locality data, causing pollution. And if we spread the data across the cache, we just maximize the pollution effect. So in our solution, we manage the memory mapping in two ways, with each one with a different cache resource allocation policy. The first mapping is called the open mapping. Just like the traditional method, it helps the data spread across cache size. And the other mapping is called the restricted mapping. It maps the user's data into a small portion of the cache, what we call the cache jail. So if we apply the restricted mapping for the polluter chunk, we can control the pollution effect at the minimum level. So here's what we have got so far. We classify the chunks into two categories, and we have two types of memory. And the open mapping is used for the cache-friendly chunks, and the restricted mapping is used for the polluter chunks. Here the question is, how do we know the chunks type? We cannot classify them. We don't know whether the chunk is a polluter chunk or a normal chunk. So in order to classify a chunk at runtime, we have to sample the data access locality, sample the data access and estimate the locality. Since the Malloc system is a core routine of the standard library, the sampling process should be lightweight and should be built upon commodity hardware support. In our solution, each sample contains a pair of page access, and we record the number of cache miss in between. We compare the cache miss with the total number of cache blocks. And if the number of cache miss is larger, then we're safe to say that the second page access is a cache miss. For real workloads, we found most of page accesses actually clustered into the burst access intervals. So in most cases, the two page accesses in the sample will be very close to each other. So this samples actually not meaningless for us because the second page access comes too quickly and it can hit the cache no matter whether we use the open mapping or the restricted mapping. So it cannot tell us which mapping is the proper mapping for the target chunk. So to skip the burst access period, we stop the page access detection until the number of cache access reaches the number of geoblocks. Note that if the number of cache access is less than the number of geoblock, it is quite likely that the second page access can hit the cache even though we apply the restricted mapping to the data chunk. And this figure shows the effectiveness of our sampling technique. We collect the data trace from these programs and feed it to the simulator. We compare the cache miss estimation with the real results. And on average, the false rate is around 6%. Note that the estimation we use for the cache the condition we use for the cache miss estimation is conservative, which means we can only estimate the cache miss as a cache hit by mistake and may further classify the polluter chunk as a normal chunk. And in the worst case, the system will apply open mapping for both the polluter chunks and the normal chunks, and fall back to a traditional Malloc system. So here, for chunk that containing many pages, do we need to sample every page of the chunk? Answer is only if the pages differ significantly in their locality properties. Here's a code segment taken from the video encoding programs. At the beginning, a memory chunk is allocated for loading a frame of data, and in the main iteration, the memory chunk is divided into many macroblocks. In each iteration, the macroblocks will be processed by a same set of the compressing algorithm. So in this case, we can see the data access locality can be quite similar within single memory chunks. To verify the observation, we examine all the memory chunks that comprising more than one page in our benchmarks, and we compare the cache miss rate of this memory chunks to each of the page in that chunk. We found that over 99% of the pages have a similar cache miss rate with their chunks. So this means we can safely decrease the sampling density while maintaining the accuracy. So for a chunk with n pages, only around the square root of the pages need to be sampled to guarantee the accuracy. So for now, we have a monitor here. And in this solution, when a user's request arrives, the Malloc system will return a default mapping for the user program. And then the monitor will sample the target chunk and check whether the default mapping mismatch is access locality. If so, it will call for the remapping. And after the remapping, the data chunk will switch to the proper mapping. And this solution seems works, but there are still several problems remains. The first problem is that for many data chunks, they are short-lived, which means there will be very little time between the malloc and free, so the remapping may be too late to take effect. And the second problem is that the remapping is not free, so it actually needs copy data between pages. So if the Malloc system frequently remap data, the overhead may be overweight the remapping benefits. So to avoid the remapping, we need to know the chunks type before it is used. Here's another code segment taken from the video encoding program. Here's a big loop, and in each of the iterations, memory chunk is allocated to store a frame of raw data. And then we convert the raw data to some other format, and after that, the memory chunk will be free back to the Malloc system. And in this case, we can see that across those iterations, the memory chunk actually share the same access pattern. They all load a frame of raw data, and we convert the raw data to the same format. So we can use the data chunk. We can use allocation. We can use the data chunk allocated from the previous iteration to predict the allocation that will be happening in the future. Note that this allocation also shares a call stack. So if we have a series of allocation that share a call stack, we will get the opportunity to make the prediction. To verify this observation, we need to check two things. First one is we want to know how many of the allocations share a call stack. And the second thing is we don't know whether the allocation that share a call stack have the similar access locality. This figure shows how the allocation cluster into call stacks, and the y-axis is the total number of allocations, and the other axis is the number of chunks per call stack. As we can see, only a small fraction, which is less than 1% of chunks that do not share a call stack. So there will be a lot of opportunity to make the prediction. We also compare the cache miss rate between the chunks that share the same call stack. And this figure shows the over 90% of chunks that share the same call stack have the same miss rate. So this guarantees a very high prediction success rate when we do the prediction. So here's the result. For the 27 programs we tested, on average, the prediction success rate is over 90%. Here we put everything together. We have a locality monitor, and it samples old chunk and record its access profile. When the new request arrives, the chunk predictor will check its call stack and analyze the historical data to find the proper mapping for this request. And then the Malloc system found a piece of free memory of that target mapping type and return the memory for the user's program. And we evaluate our system with 27 programs. We classify these programs into 3 types, which are polluters, victims, and neutral. Polluter programs are the programs which have a lot of polluter chunks, and the victim programs are sensitive to the cache pollutions. And as to the neutral programs, they do not pollute the cache too much, and they're not sensitive to the cache pollution either. We for each workload we combine 4 programs from 2 categories, and we integrate our NightWatch into tcmalloc, and baseline is the tcmalloc without cache management. So to highlight the impact of the cache resource management, we focusing on the polluter and victim combinations. As we can see, most of the victim programs can benefit from our solution, and on average, the speed up can be around 20%, and for the best cases, the first combination, the speed up can be around 40%. And the figure in below shows the result of the other combinations. As we can see, there's little changes for these combinations. Because this agree with the nature of these combinations, and also suggests that our system, when our system cannot bring benefits to the user's program, it will retain their performance. So here's the overhead. On average, the overhead is less than 1% and around 3% to the minimum, to the maximum. I'm sorry, and due to the interchunk and interchunk similarity, the monitor's overhead and the predictor's overhead goes much slower than the when their workload increases. Okay. So in summary, it is not a memory matters. It is not only the memory matter in the Malloc system, and we show the interchunk and interchunk locality similarity that make efficient chunk classification. And integrating the cache management into Malloc system offers performance improvements with acceptable overhead. And you can get our source code at this website. And before we end this talk, I would like to answer one of the most commonly asked questions. That is, why the name NightWatch? So I have to say, actually, this Jon Snow and his brother have no contribution for this work, and actually it means the system helps the program protect the cache from being polluted. So thanks for your attention, and sorry about the Chinese pronunciation of my talk, and I'm happy to take your questions.
Okay, I have a silly question because I'm from Facebook. Why tcmalloc?
Because we found tcmalloc is the most efficient one among existing allocators, so we use it. We also apply it to the glib tcmalloc. Yeah, I think it's ptmalloc 3. Yeah.
So I have a question about your applications. You classified polluter and victim at the application granularity in the end towards when you did your evaluation. Am I understanding that correctly?
I'm sorry?
So you classified at the application granularity that some applications were victim and other applications were polluters and neutral.
Yeah.
But you took the entire application, right?
Yeah.
But early on you spoke about chunks being either polluters or victim, and I'm wondering, it's actually a two-part question. One is that within the same application you could have polluter chunks and victim chunks.
Yeah.
Do you have any data that shows that's possible, or and how your system reacts to that? That's one part of the question. The second is the dynamism. Can the same chunk be victim first and then become polluter eventually, depending on how the program uses the memory?
Yeah, that's a good question. And for the first question, actually, our system actually supports the single program, such as the multi-thread programs. So the situation actually is the same. If the polluter chunks and the normal chunks are accessed simultaneously, they can benefit from our solutions. They just like the multi-program test we use in our evaluations. So, and for the second program, so is you mean when the chunks type varies when the time goes,
yes.
Then how to handle it?
Yes.
Yeah. So if a system found that a chunk switches rows very frequently, then it just uses the open mapping. Yeah. Since we don't want to let the system performs worse than the original, than the traditional Malloc system. So the design policy of our system are actually all the conservative. So when they switch their roles, we just use open mapping.
Okay, thank you.
Okay, thank you.